tell us about the characteristic Cauchy problem. And Professor Krushil is, of course, no stranger to this entire community of mathematical relativists, and has worked in several areas in, not only in the initial value formulation, but also in much more general questions in Lorentzian geometry. So it's a real pleasure to have you here with us today. So please.
So, good morning, everyone. It's a great honor to be able to pay homage to Yvonne, with whom I had the pleasure to collaborate and write several papers. So 100 years is a rather impressive age, and so we wish you many, many more, Yvonne, should you see this video. So my talk is going to be very boring about the basics of the characteristic Cauchy problem. Maybe at the end I will, add some details about current research. But of course, one has to start with the birth of mathematical relativity, which I date to 1952 at the time of the thesis of Yvonne. I think you've seen this already in previous talks, and but I will not restrain myself from recalling that Einstein equations can be rewritten as a set of hyperbolic equations and a set of constraint equations, and that particular way information was actually provided to us by Yvonne in her thesis. Well, you can do constraint equations on an initial data surface which is space-like. Then you have data, a Riemannian metric, and its time derivative, which we call Kij, or you can do it using characteristic initial data. So here, this is a picture I'm very fond of. This is, we had a conference in Cargès in 2002, 50 years of the Cauchy problem. And so you can see in this photo a dog whose name I don't recall, but then Bobby Pike sitting next to Yvonne, sitting next to Helmut Friedrich, sitting next to Robert Bartnik, and the before last person is Nicholas Delianakis from the ERC Commission. This was actually funded, this conference was co-funded by the ERC. And well, I'm also there quite a few years younger than now. So, well, the great theorem 52, solutions of the Einstein equations can be constructed by solving a Cauchy problem, a space-like Cauchy problem. Another great theorem from 69, existence and uniqueness of maximal causally well-behaved solutions of the Cauchy problem. So Cécile discussed this in detail yesterday, so I'm not going to say anything more, except that mentioning that here you see Yvonne and Jim. So Yvonne is ringing a bell, saying, well, we have to go to the lectures now. And here actually is Bob Garage during a Sunday trip. So this talk is about the characteristic Cauchy problem, and we're going to, there are two possibilities here. One being two transversally intersecting null hypersurfaces. So this is a two-dimensional version of the problem, but you could think of this as well, actually two-dimensional objects in a, well, four-dimensional, well, actually this is two-dimensional, but this is three-dimensional object in four-dimensional space-time. And an option also is the light cone, right? So in 2 dimensions, a light cone and two intersecting null hypersurfaces, same thing, but in higher dimensions, of course, it's different. In fact, one could imagine other cases where you have something like maybe a curve, and you have to, well, this is actually what you would see. Well, it's hard to visualize, right? But so this picture here would be the intersection surface and two null hypersurfaces going out. But you could also imagine this curve being in a curve in 1 dimension higher, and this null hypersurfaces being null hypersurfaces as higher dimensions, right? So that nobody has tried to do something like that. What I'm trying to say that here you have a 2-dimensional surface on which these null hypersurfaces intersect. Here you have a point, but you could have null hypersurfaces emitted from a curve. That's something that has never been looked at, and maybe there would be some interest in doing this. Good. What more can we say about this characteristic problem? Well, the early work, I think the first time I've seen in the literature something about the characteristic Cauchy problem is the paper by Sachs. That's the same Sachs as Bondi-Metzger-Sachs, and this was a paper following up on the famous setting up of Bondi coordinates and discovering the Trautmann-Bondi mass loss formula. Well, Sachs realized that this is actually a right setting for the characteristic Cauchy problem, but he didn't do much more about it. In 1966, Cagnac, that was an interesting character, a French priest who went to Cameroon, and he essentially, while being a priest, also founded the School of General Relativity in Cameroon with many students. So his PhD students and PhD so PhD sons and PhD grandsons and so forth are still active there, and actually form this Cameroon School of Research in Mathematical General Relativity, and they're pretty much continuing to do work on the characteristic Cauchy problem. Well, so this Cagnac started trying to prove theorems about it, with obviously an eye out for general relativity, but he was more setting up the basis for proving theorems about it. Müller, Zumhagen, and Seifert, well, that's the theorem which they claimed existence and uniqueness of the solution of the characteristic Cauchy problem. Well, I think that they had introduced some functional framework, and the claims about general relativity were not completely, let's say, gap-free. Let's put it this way. So the Christodoulou and Müller-Zumhagen, a few years later, so improved the functional framework, but still no clean existence theorem. Friedrich was pointing out in 81 that there is a problem with the existence in these papers. That's these 81 papers, that's where he introduced the conformal equations and proved the uniqueness theorem for the characteristic Cauchy problem, but made it clear that that there is still a gap for existence. Well, this gap was finally settled by Randall. So Randall works in 3+1 dimensions, the physical dimension. He considers two hypersurfaces, so null hypersurfaces intersecting transversally. So this is a 3-dimensional object in a 4-dimensional spacetime, and he produces an existence theorem for Einstein equations in a neighborhood of the intersection. Right? So you're giving some Cauchy data here, some Cauchy data here, and well, at this stage with Alan's work, you just got a neighborhood of this intersection surface for the solution. Well, in 2009, I started working with Ivan on this problem, and we proved a theorem which I'm very proud of. This is, we call this the light cone theorem, and the theorem is the following. Suppose you have a light cone. So a light cone is, of course, a characteristic of the surface. And now you take, so you have a vertex here. So you can start shooting finely parameterized null geodesics from this point. As you know, there's a lot of freedom when finely parameterizing a curve. So, of course, what you're going to do is you're going to say that at this point, the affine parameter is 0. Now you choose a time-lag vector here, and you parameterize you normalize the affine parameter so that the scalar product of your null generators with along this curve, along the direction of this, the scalar product of the direction of the null direction with this time-lag vector is, say, -1 or something like that, a number, and then this defines uniquely the affine parameter on all generators of this light cone. And so then you look at the surfaces of constant affine distance from the origin, and you measure their area. Okay, so these are, so the light cone is three-dimensional. Surface of constant affine parameter is two-dimensional, except of course at the origin. And so these are spheres. You measure their area, and what we show that if the Einstein equations are satisfied with matter satisfying the usual positivity condition, then this area will be smaller than the one in Minkowski and will be equal to the one in Minkowski only in vacuum. So if the area here is equal to the Minkowskian one, so I guess 4 pi r squared or something like that, then space-time will be vacuum inside this light cone. And the initial data will be Minkowskian on this light cone. So this will be a light cone in Minkowski space-time. Otherwise, this area is strictly smaller. Right? So this is I like this theorem because it gives you a very clean geometric interpretation of the shrinking character of Einstein equations, right? The positive energy shrinks space-time, and this is a very precise statement to this effect, right? So the surfaces of constant affine distance become smaller if there is matter or if there is a gravitational radiation falling through this, coming inside through this light cone. Good. So we started looking at this problem in quite a generality. So that was our first result on this. And then there was a question of, let's see, so there seems to be some kind of, okay. So Cagnac is actually at the wrong place. So Cagnac in 1980 was actually already interested in the question, can you construct, what are the right initial data on characteristics on a light cone, right? So of course, I'm going to tell you more about what the data are on any characteristic hypersurface, but of course a light cone is very specific because there is this very specific singularity here. And so Cagnac already in 1980 started looking at the behavior of the singularity here. At this stage, when we wrote this light cone theorem, this was a theorem assuming that we have a light cone like that, but we didn't have a good existence theory for solutions with characteristic data and light cone yet. So in any case, what we did a couple of years later, this is this work with Yvonne and Jose Maria Martin Garcia, then this is existence near the intersection in all dimensions, right? So Alan did this problem in dimension 4 space-time dimension, and so we just reanalyzed his proof and maybe brought in a new perspective to some aspect of his argument, and certainly showed that this works in all dimensions. Now, there was an issue which was open concerning the following. If you give initial data on this hypersurface here and this hypersurface there, you'd like to get a solution near the hypersurface and not only near the intersection, right? So this question was open until 2011, when Jonathan Luke showed that actually you do have a larger existence region. So not only this intersection, but you can go up in a strip near the initial data surface. And of course, the way to think about this is that if you choose an epsilon here, which is this width of this region, then you can go some distance, and you make a smaller epsilon, you can go a little further, and you make a smaller epsilon, you can go further, and so forth. So at the end, what you get is, given a hypersurface, a characteristic hypersurface like that, you're going to get a whole neighborhood, right, of a solution which exists in a whole neighborhood of the surface. And this was done in 3+1. And there was a very specific reason why it was 3+1, because it was using a formalism which wasn't at the time obvious how to repeat this formalism in higher dimensions. Well, the formalism that Alan was using it wasn't a big problem to generalize it to higher dimension, except that you still had to do quite a bit of work to make sure that this works. So this is Luke's theorem in 3+1 dimensions, and Luke's theorem didn't allow you allowed you to go all the way to scry. So if you are in an asymptotically flat spacetime, you have your scry in this direction. So what Luke was giving you is a neighborhood like that, where the solution exists here. And but what you can show using the Friedrich theorem, and that's what we did in 2016, that you get actually also a piece of scry, right? So you can actually get not only a thing which asymptotes to scry, but like that, but you get, if scry is here, you get a piece of scry. And of course, if the data are small enough here, you're going to get maximal development using then the Christodoulou-Kleinemann theorem. So if the data here are sufficiently close to Minkowski, with our theorem, you get a piece of scry, then you can put in a hyperboloid here, and you can use the existence theorem of Christodoulou and Kleinemann for small data to get a future development. So that was a useful thing to have. Luke wouldn't didn't claim that you can, his method didn't give you something like that. Okay, so now finally, I mentioned to you that we are interested in the behavior of the space-time of the initial data near the vertex. So we had various partial results in 2011 about this, and finally I proved a clean existence theorem. What are the right data in this region to get existence and uniqueness of solution of this characteristic problem near the light cone. 2018, that was another development. I meant there was this Luke theorem, which works in 3+1 dimension, which gives you a neighborhood of the initial data surface. So the right picture is what I already said. It would be something like that, right? But this was in 3+1. And Rodniański and Schlappenberg-Rothman showed that the techniques he was using actually do generalize to higher dimensions. So this uses this specific double null foliations with decomposition of the Riemann tensor. This decomposition of the Riemann tensor is specific to 3+1 dimension. So the one that Luke was using. So one could have the impression that 3+1 was important, but actually it wasn't. So one can actually recover a lot of this formalism in higher dimension as well. And so I think that this absolute highlight of this characteristic method and fairly recent, this is this Aretakis-Zimek-Rodniański characteristic gluing theorem, and I'm going to say you more about this. So shortly. So this is an overview of the history of the problem. Now let me present you some of the results of this paper, where you can read both something about the history, but also how to construct in detail this characteristic initial data, and that's what I'm going to tell you now. The basic theorem is this one, and this is a rather satisfactory result, I think. It is nice because it just minimizes the number of constraints you have to take into account. So again, the setup here is two transverse hypersurfaces. One is called N1, one is called N2. And what are the characteristic data? So if you look at the box, the standard wave equation, so if you have at t equals 0, the data will be phi and t equals 0 and d phi over dt at t equals 0 for a space-like surface. If t equals 0 is space-like, this will be the initial data that you have to do to use, and something similar happens for general relativity, right? So then the equivalent of phi here would be the metric, and this would be the k-tensor, right? So now if you are in the characteristic version thereof, then you actually don't have all this. You only prescribe the value of the function. So this is if you had just the wave equation in general spacetime, that you would have to give phi at n1 and phi and n2 as your data. And so the value of this function phi on the surface and the value of this function phi on the second surface. And that's what gives you a unique solution. So both solutions both exist and are unique. And the only thing you need is actually, so suppose you take a smooth function on n1, a smooth function on n2. You just require that they match continuously here or smoothly in the transverse directions, right? So if you remember, this is the intersection here is a codimension to some manifold. Well, so if the functions here match, if you look at the restriction on this intersection surface, if it coincides, then you get a smooth solution, a unique solution. Something similar happens in GR now, where now the data are the metrics, and you can freely prescribe the metric. So this G bar means that I'm actually restricting this to the hypersurface, right? So this G bar to 2 is this 2 component of the metric. And so let's see, let's look at this equation 326a. What is so special here? If you set x2 equals 0, so if you look at the tensor induced by this G at x2 equals 0, then this is gone, this is gone, this is gone, and you end up with a 2-dimensional tensor, or n minus 2-dimensional tensor in higher dimensions. So this tells you that, well, let's just stick to 3 dimensions for definiteness. Then you have a 3-dimensional surface, which is x2 equals 0. If you look at the induced tensor, then this tensor will actually have signature 0 to 2, because the x1 coordinate, which parameterizes this surface, so this, let's see, so this is n1 is x2 equals 0, and so x1 is tangent to this a parameter on the surface. Then this is a null vector field, right? So if there are no dx1 square terms in this metric, so the length of this vector dx1 is 0, and it's actually orthogonal also to the xa directions. So there is no 1a components of the metric. So this is a null hypersurface. That's how this is encoded in this, right? So, but other than this being a null hypersurface, this function g22, g12, g2a are completely arbitrary, right? So you're free to, well, let's come to the constraint, but so these are your initial data on this surface N1, and you'll have analogous data on this surface N2 here with x1 and N2 interchange. And there is a constraint that this is the Raychaudhuri equation. So this is the Raychaudhuri equation. So tau, we call tau, so tau is the expansion. Tau of this null hypersurface. I'm going to write down formula for this shortly. In fact, I can just try to show you right away what it is, right? So this is tau. So you have this 2-dimensional metric here. You just get rid of this artwork. So you have this. This is my 2-dimensional metric, and in this slide it's written as G check, so that to make it clear that this is not the whole metric, but also only this, say, 2-dimensional part of the space-time metric. So the space-time metric is written again here. So tau will be just the trace of the derivative of g along the surface, right? So normally it's called theta, and when we were writing this, Yvonne had various notes on this in which she wrote tau, and there seems to be some kind of delay between what I'm saying and what's on the screen. So she called this tau, and when I suggested, well, why don't we use theta for this, because everybody calls it theta, then she says, no, it's tau, and of course you don't discuss with Yvonne at this stage, so it was tau. So tau is the theta, and this is so the trace of the radial derivative of GAB in this other notation, or if you have these two coordinates x1, x2, because you had to differentiate between these two surfaces, that would be the derivative, trace of the derivative of this along the null directions on the surface. Well, it satisfies this Raychaudhuri equation. So you have one Raychaudhuri equation on this first surface, and you have another Raychaudhuri equation on the second surface, and that's it. So you give your arbitrary functions here, as long as it satisfies these Raychaudhuri equations, you get both an existence and uniqueness. Well, the original theorem in a neighborhood of the intersection, but then we have this theorem in the neighborhood of the surface now. So what's the geometric framework here? So let me just then try to describe you the geometric picture. So characteristic data, well, this is our characteristic surface, right? So characteristic surface, what is it? It's a 3-dimensional manifold. At the end, it's going to be a submanifold of the space-time, but of course, to start with, you don't have a space-time, right? So you want to construct one using characteristic initial data. So you start with a three-dimensional manifold, and on this manifold, you're going to get a tensor field which has signature 0 plus plus. So it's not a metric. So I'm going probably sometimes to talk about the characteristic metric, which doesn't make any sense, but by an abuse of language, or I forget myself. But so this is not a metric, right? So normally, if you have a space-like or time-like hypersurface, you have a space-time metric you induced on your hypersurface. Either well, if the surface is space-like, then you're going to induce a Riemannian metric. If the surface is time-like, you're going to induce a Lorentzian metric. Well, here you are in this case where you have a null hypersurface, and then what you're inducing is a tensor field which has signature 0 plus plus. Well, plus plus in my signature convention could be minus minus if you are a particle physicist, but mathematical generativity, you're not allowed to use the signature plus minus minus minus. It's wrong. Good. So three-dimensional manifold, this degenerate tensor, but it has a specific structure, right? So you have a one-dimensional every point of this. Well, you can look at this as like that, but look at this like that. So at every point of this surface, you have exactly one direction, which is null, and the other directions are positive. Now, lambda is a connection. So the kind of things you are used to, you know what the Levi-Civita connection is, but the Levi-Civita connection, you can define it when you have a non-degenerate metric, because if you remember the formula for the Christoffels, there is the inverse metric coming in, right? So here, with such a tensor field, there is no natural connection, and there is an extra piece of information you have to add. And this is this lambda. This is not a connection on anything, but so you have this null hypersurface here, and you have the generators. So generators are these directions where the killing vector, well, this vector, one says the radical of this G, right? But so this is the direction where the metric degenerates. And then, so you can take the integral curves of this direction. That's called the generators of your null surface. And so this is a one-dimensional submanifold, and it carries a bundle, right? It carries a bundle, which is the, so this is the bundle of directions tangent to this surface, right? So a one-dimensional bundle. And on this one-dimensional bundle, you can define a connection, right? So you can differentiate the vector L. Well, you can differentiate it either in directions tangent to this bundle or in the transverse ones, right? So this is a connection. So that's something like the Christoffels, except that you don't have Christoffels. So of course, you can always talk about Christoffels of this two-dimensional matrix, right? So this one has its own Christoffels, but from 3 dimensions, you have to add this extra piece of information, and this is included in this form lambda, right? So if you differentiate the vector L, which is in the kernel of this tensor field, then you can differentiate it with some directions, and the formula is that, well, there's a new normal formula for a partial derivative, but there is an extra piece coming from the connections, and that's described by this lambda. So that's the geometry of the characteristic initial data set. And so let's think in terms of adapted coordinates, where our surface is u equals 0, right? So r is a parameter along the surface, so r will be tangent to the generators, and the surface is u equals 0 or u equals 25, something like that. So you have GUU, G0A, no dr square terms, no dxA and you have this two-dimensional metric JB dxa dxb. As I said, this works in any dimension. So the shear, we've already said what it, well, the tau or theta, that's the expansion. The shear is the trace-free part of the derivative of this metric along the generators. And we're going to write kappa for this connection lambda, right? So if you remember, we have this connection lambda here. It tells you how to differentiate vectors tangent to the generators. And when you're differentiating in terms of in the direction dr, that's the connection coefficient kappa. And now note that if r is an affine parameter, then the derivative of the tangent direction in with respect to itself would be 0, right? So kappa is actually 0 if r is an affine parameter on this thing. And but we don't know this, right? I mean, we don't need to work with affine parameters. We can use any parameter we want on this. And therefore, and this changes as a connection coefficient then. And the Raychaudhuri equation written in terms now, which I've already shown you, but so once again, derivative of tau, which, by the way, would be a second derivative of the metric if you differentiate this once, plus kappa times tau itself. So when kappa is 0, then this term will be drop out. 1/2 tau square. The coefficient here will be actually 1 over n minus 1 or something like that in higher dimensions, where n is the space dimension, right? So in space dimension 3, you get 1/2. Square of the shear tensor and the contribution from matter fields. I'm going to assume in whatever follows that either this is 0 or certainly the positive energy condition is satisfied and this is positive, right? So if you are more used to Raychaudhuri equation, as you know, all participants from India should be very proud of this Raychaudhuri equation, then usually you see it without this term and maybe without this one again when you are in vacuum. So this is a constraint equation for this initial data. And this connection lambda, which I mentioned already before, so this is the connection along these null generators of this null hypersurface. Then you can also differentiate the vectors tangent to this generator in the transverse direction. So that's what I'm doing here. And well, just for, there's this awkward coefficient -1 psi a, right? So that's why I didn't write this as kappa or psi or anything like that, because we're using, for historical reasons, so we are just using -1/2 here. Of course, you could call it psi a, then just some coefficient will change in this equation. But other than that, it's just a notation, right? So lambda was a connection, had 3 terms. So lambda had kappa in the dr direction and -1/2 psi a in the transverse direction. And this is, as you can guess, from the fact energy momentum tensor, this specific components. So this is a tangent component to the generators. This is a transverse component to the generators here. And so this is exactly this would be the Einstein tensor on this hypersurface, and it has a direct writing in terms of the shear of this tau or theta of this kappa, which is the acceleration of the geodesics of this generate. Well, these are geodesics, but not necessarily affinely parametrized. So this will vanish if they are affinely parametrized. So this is the equation how this connection is transported along these generators, right? This is a transport equation. It's telling you how to move this connection along the generators. So this is, there are two equations because, of course, there are two components of psi. And also you get a transport equation for the other expansion scalar, right? So tau was the expansion scalar for this hypersurface, but you have, if you have the other hypersurface, which now it's going to be difficult to draw it here. So, well, let me just not try to make it in more dimensions, but if we just look at it face. Well, we take a cross section, so we have the generators here, generators there. You have a tau was expansion here, where you have a corresponding expansion here, and so it's going to become an equation actually for how this other expansion changes along this hypersurface. So from this point of view, that's the geometric part of the equations. And you can also add to this transport equations if you require harmonic coordinates, right? So that's what Alan Randall was doing. So you ask that the coordinates that you're using are harmonic in space-time. This adds you 4 transport equations. But you don't have to. The geometry here is really Ray-Chaudhuri, this transport equation, and another equation for the other tensor, and here they are, right? So this is the Ray-Chaudhuri equation we just talked about. This is transporting the transverse part of the connection. The kappa part is completely arbitrary. That depends upon the normalization of your parameter. Could be 0 in the affine parametrization, and this is the equation for the remaining expansion. But the remaining expansion has its own Ray-Chaudhuri equation here, but along the surface, it satisfies this transport equation that I wrote here, right? So as you see again, once you have sigma and kappa, you can calculate tau by solving this equation. Now, once you have sigma, kappa, and tau, so you have kappa known, tau is known, sigma is known, you can calculate psi a. And once psi a is known, R is the scalar curvature of your metric of these two-dimensional surfaces. Say it's vacuum, it's gone. And well, we might have a cosmological constant here. Well, psi is known from 213, and you can calculate zeta, right? And the remaining equations, I'm not going to tell you much about them because they have a coordinate character. So the equation 212 and 214 and 216, they satisfied when you're imposing harmonic coordinates, and they have to do, there are various parts which are related to these harmonic coordinates, but you don't have to ask that the coordinates in spacetime are harmonic. There are many other ways to do it, and therefore these 212, 214, 216 are not geometric equations, but 211, 213, 215 are. And so before I continue, let me mention something very useful, the system of coordinates introduced by Eisenberg and Moncrief. So Eisenberg and Moncrief were interested in, let's see, compact Cauchy horizons. Now, compact Cauchy horizons are null hypersurfaces, and so they devised a coordinate system which was very useful for their purposes. And the reason why this coordinate is very useful is, first, it encodes the characteristic properties of this hypersurface, and when you write down Einstein equations in this coordinate system, they have a particularly nice form. So you don't have to use Heisenberg-Moncrief coordinates. I told you you can use any coordinates you want in space-time, but if you use the Heisenberg-Moncrief coordinates, well, first the metric takes a nice form, and second the metric. So I'm not going to show you the coordinates here. If you want to see them, well, you can find them in the Heisenberg-Moncrief paper, or some papers I'm going to mention to you later. For instance, a paper we wrote. Well, actually, we posted in January this year with Wan Zhang and Finian Gray, where we write down the full Heisenberg-Moncrief coordinates in any dimension. So and they are particularly suitable for the analysis of the problem if you want to do some analysis. So how does this work, right? So somebody is requesting remote control of my screen. I have this message here, and I'm not going to accept this. Why is someone? Why would?
Yeah, I cannot see that. But
okay, yeah, you can't. Yeah, it's a Zoom message. I'm going to decline this, but this is unexpected. All right.
Okay. I'm sorry.
I understand you still hear me, right?
Yes, we can completely hear you. Everything is
okay, very good. So Heisenberg-Moncrief coordinates. Your surface, the initial surface n is u equals 0. That's what I was calling u n1 before. There's another one which is transverse, which is again characteristics. So this one is u equals 0. This one is r equals 0. Now, if you look at this metric, at u equals 0, this drops. U is equal 0 here. This drops. U equals 0. This drops. So you're left again with this two-dimensional metric GAB, or higher dimensional Riemannian metric on the sections of this surface, right? So this is at u equals 0. This is a null hypersurface. If you look at r equal constant surfaces here, these are all characteristic again, because if r equal constant, then this, whatever multiplies this, drops out, because dr is 0, and you are again left with this. So every r equal constant surface is characteristic. So these ones are characteristic. But it's not true that every u equal constant is characteristic. Only u equals 0 is characteristic, right? So this is not a doubly null coordinate system. There is another coordinate system which is doubly null, which is used by Aretakis, Timek, Rodniansky, Christodoulou, and so forth, that it has a lot of interesting features. But this one, well, one has to keep in mind that the world is not necessarily doubly null. It's not necessarily Bondi coordinates. It can be Heisenberg-Moncrief coordinates, and they're useful for the purpose. But the hypersurfaces here are not all characteristic, right? But the initial ones are. Okay, so this alpha here is actually exactly kappa of my previous slides. So I use a different notation because alpha is a really a function of space-time, while kappa was only a parametrization of the initial geodesics, right? But alpha is actually kappa. It's not clear, one has to check that. And because kappa is a gauge quantity, in particular, can be set to 0, alpha can also be set to 0, right? So you can even simplify this a little bit, but probably there's no need to. You can just work with general Heisenberg-Moncrief coordinates. So this is Randall's theorem in terms of Bondi Heisenberg-Moncrief coordinates. That's a clean way of presenting it. So what are the Cauchy data for in Randall's formulation? Well, he takes on the intersection of these null surfaces. So here, this is our intersection. So on the intersection, you prescribe this one form beta, right? So you have to prescribes this one form beta. That's a free data on the intersection. And on each of these hypersurfaces, you prescribe freely G, and you prescribe, well, freely, again, that'll be the Ricciarduri equation, but you prescribe JB and you prescribe this function alpha. You want to, maybe you want it to be 0, fine, you don't have to. Okay, so you give yourself this data, and they're subject to the Ricciarduri equation. Now here, trust me, this is again the Ricciarduri equation, but now written in full in terms of G and of alpha. Right? Before I was writing it in terms of tau, kappa, sigma, and so forth. But if you only think in terms of these fields, then this is how it looks like. So these beta is completely free on the intersection, but alpha and G have to satisfy each on each surface their own Ricciarduri equation, and this gives you a solution of the equation, which I already discussed, in a neighborhood of the intersection, right? So this is the intersection, and you get an intersection. Luke has pushed the result to a neighborhood of the surfaces in 3+1 dimensions, and Ivan, myself, and Jose Maria, we just first proved the result near the intersection, and finally Rodniański and Schlappentok-Grothman cleaned this up and proved this in a whole neighborhood in any dimension. It's actually a very embarrassing paper that I posted last year. I wasn't aware of the Rodniański-Schlappentok-Rothman paper, and we were interested in generalizing, therefore, this 3+1 result to any dimensions to get the full neighborhood, and not only, so neighborhood here, not only neighborhood of the intersection. And we wrote a paper showing how to do this. And when we were just about to post, then, so this was with Finian Gray and Roger Wafo from Cameroon. So Roger discovered that Rodniański-Schlappentok already did this. So that's very disappointing. But anyway, so if you're only interested in seeing how to generalize this in high dimensions, we have a preprint on arXiv, but I don't think we're going to publish it or anything because it's essentially already in this paper. Good. So recall Ricciarduri. Already told you that alpha can be gauged away, so you can, and that alpha is actually kappa. Now, Randall adds something else to his theorem. He says that, well, this GAB, you can use a characteristic conformal method, right? So conformal method is something very popular for the space-like Cauchy problem. Well, he proposes a conformal method for the conformal one, where this metric JB, you prescribe its conformal part, and you leave a conformal factor free, and then this Ricciarduri equation can be rewritten as a second-order equation for phi. So now, when you do this, well, he proposes to take 0 here. Why not? And he says, give any conformal class, then this Ricciarduri equation, well, you get second derivatives of G, but second derivatives will be second derivative of phi plus second derivative of this, but this is known. So this becomes a second order equation for phi. And then your free data are essentially this conformal class. You set to 0 and you solve your Ricciarduri equation. You have no constraint anymore in this case, right? So it's like, of course, the constraint is there, but he's proposing a way to solve this constraint. Christodoulou says something else. Do not prescribe the conformal class of this metric G, but prescribe the shear, right? Prescribe the shear. Well, what is the shear? The shear is the trace-free part of this derivative, right? So you look at this equation, prescribe the trace-free part of R. So just take this equation, decompose every derivative in its trace-free part and its trace. You get the standard form of the Raychaudhuri equation. And he says, well, why don't we use DRGAB as free data? Right? Now, this is sounds very reasonable, except that when you say trace-free, well, what is trace-free, right? So we have a tensor which is trace-free. You have to have G. But you don't have G because you have to solve this, right? So yes, you can do this, but then you need a frame, right? So rather than using a coordinate formalist, you need a frame formalist. So then in this case, well, the metric is just diagonal entries 1, 1, 1. And you know what trace is if you give a tensor in this frame. So you give a tensor in a frame, the frame you don't know what it is, but you're going to reconstruct it as you go, right? So you give the tensor sigma, which is in a frame, so you know what it means to be trace-free. You put it in this equation, you calculate tau, and then you have to add some conditions on how to transport your frame to get a well-posed system of equations. So this is Christodoulou. And finally, Friedrich has a nice proposition based on this equation here. So now this bar here is actually the check which we had before, so I apologize for this. This is coming from another paper. So the check, it means that you just have this GAB metric, right, on this null surface. And if you look at this equation, well, what do you have here? You have kappa, which is our usual acceleration parameter. Could be 0 if it's an affine parameter. So it's part of this connection on the initial data set. And so the only thing which enters here is kappa and the metric. And you have part of the Riemann tensor, the space-time Riemann tensor coming in here. So Friedrich says, and well, interpretation, some people think of this as describing the incoming radiation coming through this hypersurface. So you have a null hypersurface, and this is the component of the Riemann tensor, which would give you the information about incoming radiation, right? If this is 0, actually, then you could get a flat hypersurface out of this. So Friedrich proposes to use this. Again, you need a frame formalist because this A is a trace-free tensor field. So in a frame formalist, you can use this as free data, calculate this DRGBD out of this, and because this is a trace-free, actually this involves only the trace-free part of G, and then you can use the Raychaudhuri equation to get your theta and so forth. So I think my time will be up in 2 minutes. So let me see if I can only tell you right. So the last thing I want to mention to you is this Aretakis, Ziment, and Rodniansky gluing theorem. So that's the latest development in understanding the Cauchy problem. And what is this theorem about? Suppose you have a space-time G1, the yellow space-time, which has a boundary. The boundary is a null hypersurface, right? So you have a null hypersurface and a space-time G1 in a space-time region with the geometry described here. Note that normally we think of having a characteristic Cauchy problem, we would need a second hypersurface here. Maybe you have one, maybe you not, you don't care. You have just a yellow space-time like that. Now here you have another space-time, the green space-time. Again, a null hypersurface here. And it is, well, by the way, this is a null hypersurface as well. And well, it doesn't have to, but it makes sense to make it more. And here you have a space-time boundary characteristic, and again, a null hypersurface to the past. So you have a yellow space-time, a green space-time. Think of this as being, for example, Minkowski, and think of this as being an extreme Reissner-Nordstrom black hole, and then this being an event horizon of an extreme Reissner-Nordstrom black hole. That's actually an example which has been looked at by Andrew and Keller recently in a nice theorem, which I'm going just to mention very shortly in a few minutes. So the question asked by Aretakis, Zimmer, and Roniański, can you find this red piece of null hypersurface, which will join smoothly these two, and my time is up, with these two hypersurfaces. Now, once you have that, you can construct a whole space-time which contains both a new space-time which contains both the yellow and the green one. Okay, so that's the Aretakis, Zimmer, and Roniański gluing. The answer is yes, you can kind of do it with some constraints. So you have to, there are abstractions, and they show you how to get rid of these abstractions if G2 is coming from a family of metrics like a Kerr family or something like that. And I'd like to emphasize that I think that this is one of the most important developments in general relativity, mathematical relativity in the last 2 years. Well, of course, if you add to it, one shouldn't forget the stability of Kerr, which has also improved recently, but somehow perhaps before or so in any case, that would be one of the highlights of mathematical GR. Now, so let me just go quickly to the Unruh and theorem, which I'd like to advertise, which is somewhere up there, obviously very far away. Yeah, so this is last year, using this gluing method invented by Aretakis, Zimmer, and Roniański, the third law of black hole dynamics is wrong, right? So there was this third law conjecture: a black hole with zero surface gravity cannot be formed in a dynamical process. And Keller and Unger, using this characteristic gluing techniques, showed that this is wrong, right? So constructed a family of examples where you form a zero surface gravity black hole using from data which don't contain one. So yeah, as I said, my time is up, so I'm open for questions.
Thank you very much. Let me clap for a really nice talk. It was just the right level of pedagogy, not boring at all. I think.
Thank you very much. You're very kind. I mean, I was trying to convey, the
I think it's new.
Basics of the problem,
and
if somebody wants to work in it, then maybe you can start from the information
here. Was,
look at the papers.
And there were lots of new results that many of us were just not aware of. So it was really a very nice summary. We're open for questions. Is there anybody? I don't know if they've sent. Okay, there's a question by Sucheta Majumdar. Please go ahead, Sucheta.
Hi, can you hear me?
Yes, I can. Yeah. Hello.
Yeah, thank you for the very interesting talk. I have sort of a half-baked question, but I'm going to ask it anyway. So if I understand correctly, your results hold for any generic double null foliation, right? Where you have an N1 and N2 and a codimension 2S. So, but in your case, the S is always a sphere, right?
No, right. So I mean, right. So I'm not sure what Randall assumed, whether he assumed a sphere, but Now, at this stage, certainly, Aretakis, Tsimetrodniansky assumed a sphere in 4 dimensions. You can take any hypersurface and in any dimension, you have the same results.
Oh, okay. That's very interesting, because the kind of system I'm thinking of is some planar null coordinates, say t plus z, t minus z. In that case, the codimension 2 would be an R2.
Right.
So I was wondering if one could extrapolate your results to that kind of.
So this works, and you don't need compactness. Also, it doesn't have to. So you also have these two hypersurfaces in any dimension. So if you are in 25 dimensions, each of this space-time, then each one of them will be 24, and the intersection will be then 23-dimensional, and it can be any manifold, 23-dimensional with a Riemannian metric, or it can be a light cone in 25 dimensions, and then we get tip of a light cone in 25 dimensions.
Okay, that's very helpful. Thank you.
Welcome.
Any other questions? Are there any that have come? Let me just check. We haven't had any on the chat either. So maybe I can ask a question related to an earlier part of the talk. I think this was your 2009 paper with Yvonne about the fact that you have these positive energy conditions. Then you know that there's this area increasing, right? The sectional area is increasing. So I had a couple of questions
the
about
light cone
that.
theorem. Yes, thank you.
Sorry. Yes, this light cone theorem, right? So a couple of questions. First of all, the energy conditions, I think all through when you were using energy conditions, are these
right? So what you
conditions
need to assume is energy conditions on the boundary, and then so then the theorem is true. Now, if you want to say what's the space-time inside, then you have to work a little bit to make sure that the boundary conditions, the boundary actually imply that the boundary conditions are that. So in the extreme case, right? So if you are in this rigidity case, you have you want to conclude that the metric is Minkowski inside, then of course to be Minkowski inside, you have to know that the energy conditions are also satisfied inside, right? But, yeah.
Well, so they're the null energy condition, or what?
On the boundary, you have the null energy condition is good enough, because on the boundary you only analyze the Ricciarduri equation and the other equations as well. You have to work with the other equations to show that this is a light cone in Minkowski. But but if you want to extend inside, you need the usual full
there are, of course, these generalized, integrated null energy conditions and all, which will allow violations locally.
Right. So this will probably not work. Right. Yeah.
Right. Which brings me
I don't know.
I
haven't thought about this, but the whole argument, right? I mean, you're integrating from 0 to R, and you vary R. So if you only had an integrated energy condition, I don't think you'd be able to conclude. Yeah.
Right, you'd have local violations, I suppose, but maybe one would hope globally that it would still be a positive.
Well, so one has to be careful, because to get this, that the area is nice. Well, you need to work a little bit with all the equations. So I don't. You're probably right, but I don't know. I don't know.
Okay. And related to that is one of the statements you made, that the light cone is well defined everywhere. So topologically, I mean, if you had something that had caustics and stuff, what would you do in such a situation? Or is it that
right? Yeah. So when you have a light cone, you go only all the way to the caustics. And if you have this, you only also go all the way to the caustics, right? The caustics start and hell breaks loose. Yeah.
Okay, great. Okay.
Yeah.
And I'm going to ask one more question.
Go ahead.
There are no other hands. no other hands raised, so I'll ask my last question, which was, I think, and maybe you said something about it, but I'm a little confused. This last work that you did on, which was to extend the work of Luke to Scribe Plus.
Okay.
There, you made a mention of it being close to Minkowski, is that right? Or what? I mean, I don't know. There's something you said.
No, here you don't. I mean, so right. So let me draw this again. Let's see. I just get my drawing tools. Okay. So you have a scry here, right? And so Luke tells you get this neighborhood, and we tell you actually have this, and this is always right. So always, of course, modulo caustics, right? So of course you need to have a light cone here which doesn't have a caustics, and you need and also when you need, yeah, there's this perverse case which could happen that you develop a caustic exactly at the when the light cone meets scry, right? So this is not allowed either, right? So so the cone has to meet scry in a smooth, nice section, and then you always get this this region which I've drawn here. And now if the data are small, right, then you get moreover the whole space-time.
I see.
But,
okay, so
but if they're not small, what you get, right? So probably you're going to get black holes in some situations and so forth.
okay, thank you. Thanks so much. Are there any other questions?
Well, so I
not-
have to, as I already mentioned this to Surya, I have to apologize. I cannot stay longer today because I have some engagements.
Thank you so much. Yeah, thank you so much.
Wish you
And,
good continuation for your conference. And let me just say it again. I mean, I'm very proud and fortunate to have been able to collaborate with Yvonne, and it's a pleasure to give her a little homage, my modest homage for all her great achievements. And thank you.
Thank you so much. Thank you so much for this talk. And it'll all be available on the YouTube channel soon. And so hopefully it'll continue to be a resource. Thanks so much, Pietro. And
thank you. Bye-bye.
Bye-bye. Yes. We can take a break right now. I don't know if Badri is here yet.
Yes, I'm here, Sumati.
Oh, hi, Badri. Let me make you host.
Hi, Badri. I apologize, but I have to leave. So
that's okay. Thank you, Pietro. Yeah. Bye-bye.
Let me make you host, Badri, and we have just about 5 minutes to start. So if anyone wants to, you know, take a short break, we'll be back I'll be back in a couple of minutes. That's
Okay, so I'll share my screen in the meantime.
Yes, please do, and yeah.
Can you see my screen?
Yes, I can see it.
Okay, good. So then I will wait, and then just let me know when I should start.
Sure. We can also see the sidebar if that's what you want to do, or you want to make it a full screen.
Yes, I will make it a full screen. Just a minute.
It shows a blank right now.
Sorry?
Okay, so now should be full screen.
Yeah, it is. So could you just scroll across your slides? Yeah. Okay.
Okay, good. So I'll wait, then let me know when I should start.
So we can start. Exactly 3:15, and I'm lucky that I'm at RRI, and it's exactly the time when the coffee comes in, so I was able to grab a cup before your talk. It's a real pleasure to have Badri here with us today to join us in this what's been a really fascinating conference, a very stimulating conference on predictability in general relativity, to celebrate Professor Yvonne Shakir-Bruha's contribution to the field. Badri has been at Nijmegen, at Radboud University, for several years now, and has worked on a range of very interesting problems, including working on gravitational waves. So from that end to all the way to very formal aspects of general relativity. So it's a great pleasure to have him here with us today. Please, you may start, Badri.
Okay, thank you, Sumati. So thank you really for the invitation for this conference. And as you know, I had a little bit of a scheduling problem because of teaching and the responsibilities, but this was something I just simply could not say no to. So I had to make sure that everything else had to work out. So thank you. It's a real honor to give a talk at this meeting to celebrate the contributions of Yvonne Shakir-Bruha. So the talk I'm going to give is I hope in the same spirit. So it's about black holes, but in the context of how black holes behave under an initial data set and how they behave under time evolution. And I was asked to make it pedagogical. So this should be suitable for, I think, people not familiar with the subject. So please ask questions during the talk if you have any. Okay, so let me start off with this. So this, when people think about black holes, this is something like this is what they have in mind. So this cover of Science from the 90s shows one of the first numerical simulations which managed to get the event horizon. And in this case, this is for two black holes in a head-on collision. And in fact, with Relinquist data, as I'll discuss later. And this is the event horizon. So then you see this classic, what is known as a pair of band structure. So I have these at early times. This time goes along the z-axis here. And at early times, if I take a cross-section of the event horizon, then I have two disjoint black holes. And as it evolves in time, then these two black holes merge and gives sort of a connected part of the event horizon. And putting it all together, then you get this event horizon as shown here. So now I want to criticize that figure. So not in the sense it's wrong or anything. It's just that event horizons are, of course, useful for visualizing how we think of a binary black hole merger. And it is important here that this provides a link between the initial and the final state. So initially I started with two disjoint black holes, and these merge into a single final black hole. And the event horizon sort of captures this whole process in a very nice way. However, we want to sort of do more than just visualize things here. So if you want to actually calculate numbers, so you want to calculate things for the merger itself, and this could be useful in gravitational waves and analytical studies and what have you. So for example, we would like to know how does the areas of the horizon change. So this in principle you can do here. So you can look at the areas of the two different cross sections here at early times, and then see how they increase in time as radiation falls into the black hole, and you can continue that later. But as I'll try to argue that for things like masses and for spins and for other multiple moments and so on, event horizons are not ideal. And of course, from a mathematical point of view, you'd like to prove certain theorems about how black holes behave during the merger. And also analytical calculations for if you're interested in gravitational waves, you can do that for the inspire and the ring down paths, but the merger is difficult and remains somewhat of a challenge still. Okay. So I want to argue now that, in fact, event horizons are not very useful for many of these purposes, and I'll argue that in the following way. So first, I'll define important notion for this talk, which is the notion of a trap surface. And this was first introduced by Roger Penrose in the context of the singularity theorems. So what are these things? So these are closed space-like surfaces of 2 dimensions in a 4-dimensional space. The topology is meant to be spherical, so it doesn't mean that it's a round sphere. It just means that as far as the topology goes, it's a closed spherical surface. And then I have the null normals to this surface, which I'll just denote by L and N. So L will always be the outgoing null normal, and N will be the ingoing null normal. So you should think of these as light rays propagating orthogonally from the surface, and the expansion of the null rays is what is important here. So what that means is that I take a little cross section of these, look at a bundle of light rays coming out from the surface orthogonally. I look at a little cross section of that bundle, and then look at how the area of that bundle changes. And if it's increasing as I go away from the surface, then the expansion is meant to be positive. If it's converging, then the expansion is meant to be negative. So now, for a trap surface, both of these expansions are negative. So these are all future directed. So the light rays along N, the ingoing one, is negative. So that is quite okay. If you think of a normal 2-sphere in flat space, so then in fact the ingoing light rays are converging. In this case, what is unusual is that even the outgoing light rays are converging. So this is a signature for a black hole. And this is, of course, intimately connected to the singularity theorems. So the surface that we will look at in this talk will be a limit of these such surfaces. So these are known as outer trap surfaces. And also these are marginally trapped in the sense that the theta L, the expansion of L direction, is meant to be 0, and we will not impose any condition on theta N. So you should think of these surfaces as like the boundary of the black hole region, and there are subtleties connected to this statement, but still, at the moment, this is what we are trying to capture from this definition here. Okay. So the basic object of interest for us are the surfaces which have one expansion to be 0, and the other expansion could be negative or could be partially positive. Is not so important. The important point is the expansion of L being 0. So such surfaces are known as marginally outer trap surfaces, or MOTS in short, and this is what we will look at in this talk. So now, how is this connected to the event horizon that I mentioned to you earlier? So if you look at a Schwarzschild black hole, so a simple solution that all of you would have studied in a GR course, and look at the event horizon in that case, so the cross-section of the event horizon will be these marginally trapped surfaces. But in that case, the event horizon is static, so it doesn't change in time, and what I said is true, but this is not true for the event horizon shown here. So if you were to take a cross-section of the event horizon in this case, you would find that since the area of the event horizon is increasing, that the cross-sections, in fact, are not MOTSes. So these, in fact, are positive expansion. So MOTS is actually inside the event horizon. So it approaches the event horizon at very early and very late time, but anywhere near the merger, so that will be inside the event horizon. So now I want to argue through an example that, in fact, for the things that I said before, which is I want to calculate how the areas, the masses, and so on change during the merger, I want to argue now that for the event horizon, this is actually not such a good idea because of illustrate that with this example of a Vaidya spacetime. So what this shows is the collapse of null dust. So let me just walk you through what this situation is. So depicted here in this Penrose diagram. So I start off with flat space. So that is this part in purple. So that is simply flat Minkowski space written in these null coordinates. Starting from a time in this null coordinates v equal to v0, I have ingoing infall of null dust, which collapses to form a black hole. And as the null dust falls in, you get a singularity, which is shown on the top in the dashed line, and you also get the event horizon. So now let us assume that the null dust infall continues up to v equal to v1, after which time it stops. So the part shown in red here, or is the Schwarzschild space-time with the mass given by the final mass, how much mass has fallen into the black hole. So the part of the event horizon is then the null surface shown labeled as EH, which is you start off with future null and future time like infinity, and you trace back the null surface, and then you get these solid line as shown here. So for the early part of this event horizon, early as in close to I plus, so there it is really a short shell black hole. So it has a constant area and everything is as you expect. As you go further back in time, the event horizon continues being null, and in fact, it extends into the flat region shown in purple there. So this might seem surprising, but it is simply true. So it is the case that if an observer is living in this flat region, then he or she would be, in principle, could be inside this event horizon, but they would not notice anything, and there's nothing they could do to actually locate it. It is just flat space, but there's no experiment they can do locally to locate the event horizon. So in other words, the event horizon exists in that case, and in fact, it has increasing area. So if you look at the very left part of the event horizon at r equal to 0, that has 0 area, and it's growing and it grows, reaches a final area at I plus. So in the flat region, it is increasing in area, but it's flat. So there's no infalling flux of anything there. So it is growing even though there is no physical flux of any energy into the black hole. It only grows because the event horizon is sort of a global notion. It knows what will happen at very late times. But I would argue that this illustrates nicely why the event horizon in all cases cannot be a useful physical object for the questions like the ones that we had in mind. On the other hand, if you look at the Motses in this case, and you look at the spherically symmetric Motses, so that is shown in this surface labeled as r equal to 2mv. So as the mass changes, so m of v is the mass function, so that m of v is 0 at v equal to v0, and it increases up to the final mass at v equal to v1. So that is the function m of v. And the surface r equal to 2m is the one shown, the solid line which sort of starts off at the singularity and increases all the way and approaches the event horizon. So that surface is the one which is foliated by Motses. So any cross section of that is a marginally outer trap surface, as I had defined before. And that is the one that sort of knows that there's infalling flux. So the rate at which the area of that increases is connected directly to the infalling flux of matter. So there's a lot more I could say about this example, but I just want to make the point that this illustrates in a nice way that in many situations where things are changing in time, using these Motses is a more useful way to study black holes than to use event horizons. All right, so let me go on. So now I'll talk about numerical simulations and about results of Motses, how they behave for certain initial data sets and how they evolve in time. So I want to tell you first about how we would locate these Motses. So first of all, just a notation. So the outermost margin trap surface on a Cauchy slice is known as the apparent horizon, and this is used regularly in numerical simulations. So the way this works is that I have a given Cauchy slice. So the spatial slice is sigma, the 3 metric is h, and the extrinsic curvature is k. Then I want to look for a sphere in this initial data, which has the property for the vanishing expansion of L. So the first step is to construct the null vectors L and N. So what we are given is the time is a unit time like normal t hat, and the unit, and for a given surface, I will have the radial vector r hat. So I can combine the r hat and the t hat to get L and the N. And then we're looking for surfaces which satisfy theta L being 0. This reduces to a differential equation, second order equation on this spatial slice, and you solve that to obtain the Motses or the apparent horizons in this case. Then, once you evolve the data from this initial data, then at each time slice you find a Mots, and if you stack up these Motses together in time, then you get a surface of topology as 2 cross r, and this is what is a dynamical horizon. And this, this is what I want you to think of as the evolution of a black hole in time. Okay, So I've called this in this case a margin trap tube. So this is defined as a 3 surface that is foliated by Motses. And this, in fact, is a space-time definition. And even though you might use this sort of initial data construction to locate it, but this 3 surface is a geometric object in a space-time, and it can be studied in its own right. So there's a lot of notation problems in the subject. So if you look at literature, you'll find different words to refer to the same thing. So the basic object we have is sort of a 3 surface of topology S2 cross R, as I said, which is foliated by these Motses. So this can be called a dynamical horizon, could be called holographic screens, and so on and so forth. But don't get confused. So all of this refers to the same physical object at the end of the day. There's also one more little point, which is that it's often common to assume that the expansion of the ingoing null normal is negative, but this doesn't always hold in practice, as we shall see. And yeah, so this is not an essential condition in the subject. All right. So I just want to make 1 or 2 comments regarding, again, the initial value formulation and dynamical horizons. So the first thing is that the properties of the dynamical horizon, in the case when it is space-like, and this is the sort of the typical case that happens when a black hole is formed and it grows and settles down. So it's normally a space-like surface. So it's a space-like surface. So therefore, the constraint equations hold on it. And in fact, many of the results in this subject come from analyzing these constraint equations combined with these equations for a Motz. So that is one aspect, in fact, where dynamical horizons, the whole subject and what we did relies heavily on this 3+1 formulation. And there's one more example which relates to what Piotr Kruszwil was talking about in his talk just before this, which is in the case when there is no infalling flux. In that case, the dynamical horizon is actually a null surface, and it is often referred to as an isolate horizon. And in that case, the geometry of the space-time near that is obtained by characteristic formulation, exactly like Piotr described in his talk. So I just want to illustrate that with this diagram here. So in that case, the surface here referred to as delta is the sort of the null surface, which is the isolate horizon, and it has certain cross sections, and you can construct a sort of a transverse null surface n by looking at a given cross section and looking at the past directed light rays emanating from it, right? So that gives you this cone-like null surface going backwards in time. Then, given the data on the horizon itself and the data on n, you can actually construct the space-time in this whole neighborhood near the space-time. And this is a characteristic initial value formulation, and this again is very closely connected to what Piotr was talking about just in the talk before me. Okay, so let's proceed. So I want to now think about the evolution of a margin trap surface in time. So first of all, let's observe numerically that this surface evolves smoothly in time. So I don't know of any example where I have start off with a margin trap surface and I evolve it in the Einstein equations and it behaves discontinuously or anything. The evolution proceeds smoothly, and as far as we can tell, this is a generic statement. Now, often you'll hear in the literature that, well, apparent horizons can jump, and that is true. So it is true that the apparent horizons can behave discontinuously. So, for example, when I have the merger of 2 black holes, when the 2 black holes are close enough, then there is a common horizon that is formed, which is outside the 2 individual horizons. And this can be thought of as a discontinuous process. But what's happening here is that the individual Motses, as we shall see, they all evolve smoothly. It is simply that a new Motz is formed outside. And so therefore, for the apparent horizon, which is the outermost Motz, so that behaves discontinuously. Okay. All right, so then there is actually, in fact, a precise mathematical statement, and in fact, a very interesting set of results connected to this time evolution. So this was obtained by Anderson, Mars, and Simon back in 2005. So what they showed was the following. So what they showed was that this tube of this margin trap surfaces that evolves smoothly and continues to exist, and it is guaranteed to do so if this surface S, this Motz, is so-called strictly stably outermost. So this is a stability condition. What that means is that if I deform this surface outwards on this spatial slice, then it becomes untrapped. Okay. So in other words, I look at in this figure here, the surface in red is the MOTS. I deform it slightly outwards and obtain this dashed blue surface shown with the arrows. And if I calculate the expansion for that surface, then that should be untrapped. That should be then positive expansion. If this is the case, then in fact it can be proved that the time evolution of the MOTS will produce a smooth surface. Okay, so this sort of explains why MOTS evolve smoothly in time. And in fact, as we shall see, there's even the cases when this does not strictly apply. Even then, the MOTS does evolve smoothly in time. So I think there might be room here for mathematical results which sort of generalize the time evolution of a MOTS. And it is true that there must be some weaker condition under which a MOTS evolves smoothly. Okay, so now let me, in the interest of time, let me skip this part here and let me go on to the numerical results. So the first point is that we want to locate a MOTS numerically. So what we're looking for is a surface on a given spatial slice. And the usual formalism is to say that, well, let us say that this surface is defined by a radial direction, r, which is a function of h and theta. So this equation r equal h of theta and phi refers to and defines a surface, and you want to find the h of theta and phi such that the expansion of the L vector is 0. Okay. So this implies the following. So this implies that the surface is star-shaped. What does it mean? It means that, well, I start from the center where I've defined these coordinates r, theta, and phi, and I draw a straight line from there. Then that surface has to intersect the surface, that line has to intersect the surface I'm looking only once. So that is what is referred to as a star-shaped surface. Okay. So in this case, there are 3 MOTSes here. So we'll describe this more fully, but you can just say that the 2 surfaces in red are the 2 individual MOTSes in a black hole collision, while the surface in blue is the common MOTS that is formed for the final remnant black hole. So the surface in blue, in fact, is star-shaped in these coordinates. So I start from the center, I look at the radial line, and that intersects this blue surface only once. However, there are also other MOTSes in this case, as we shall see. And the example of that is a surface in green, which has this figure 8 shaped here. That also is a MOTS, in fact, and that is not star-shaped. So if I start from the center and I look at the intersection of the radial line with that green surface, and it's not obvious here, but if you look carefully, it turns out that this is in fact not star-shaped. Okay. So this is to say that there exist highly deformed MOTSes in a given on given spatial slices, which are difficult to find by this method. So the first thing that we did was to in fact improve on this numerical method to find MOTSes. So I won't go into details here, but the basic idea is the following. So I say that, well, I define a MOTS not by this star-shaped condition, but by a reference surface. In other words, I start off with some other surface. In this case, that happens to be this blue surface here. And I define the MOTS as the distance from this surface. So now the surface is defined not by r equal to h of theta and phi, but as this distance as a function of theta and phi. And in this definition, then you can check that the figure 8 surface, in fact, is well defined. So if I look at for example, the ingoing sort of the dashed lines coming from the blue surface, that intersects this figure 8 surface only once. So that defines a suitable, provides a suitable basis for locating this figure 8 surface. So extensions of this kind of method are what we use to locate highly distorted MOTSes in our case. So let me now illustrate this with Brill-Lindquist data, which in fact is a delightfully simple construction by, as the name suggests, by Dieter Brill and Robert Lindquist in the 1960s. So in that case, the data is actually time symmetric. So on the spatial slice, the extrinsic curvature vanishes, while the metric is conformally flat. So the only thing I got to specify in this case is the conformal factor. So the metric is then this 5 to the 4th times the flat Euclidean metric. And what Brill and Lindquist showed was that, well, for the case of two black holes, this conformal factor is just of this form given here, which is 1 plus m1 upon r1, m1 upon 2r1, and then for the second black hole, m2 upon 2r2. R1, R2 are the distances from 2 points on this Euclidean space, known referred to as punctures, which you can think of as centers of the two individual black holes. And this, as I'll explain, this is delightfully simple, but there's a huge sort of rich variety of these motzes in this initial data and also under time evolution. So let me illustrate that with the following figure. So let us now think of a given Brill-Lindquist data. Let us fix M1 and M2. So now you think of the initial data here. Fix M1 and M2 and just change the distance between the two punctures, right? So as I said, R1, R2 are the distances of any point on this spatial slice from the two punctures. And let us say that D is the distance between the two punctures. So I just want to change D, keeping M1, M2 fixed. So this is sort of the numerical exercise we're doing here at the moment. So this shows the situation, for example, for a given value of D. And in this case, I've taken M1 and M2 to be 0.2 and 0.8. So the mass ratio is 1 to 4 in this case. And we're looking for motzes as I change D. By the way, if any questions, please stop me, right? Because I have no idea if people are following or not. So it'll help if people do ask questions. So this one, this figure here shows a particular snapshot of this for choice of D. And what you find here are in fact 4 motzes. So there's at least 4 motzes in this initial data. So the one in red is the mods connected to the big black hole. The one in magenta I guess it's purple, is the one for the smaller black hole. And it turns out there are in fact 2 common motzes. It's hard to make out here. There's a blue and a green one. So the blue one is the apparent horizon, the outermost motz. There's a green one which is slightly inside, which is also very close in shape and for this value of D, but that is also a motz, and it is what is referred to as the inner common motz in this case. Now you make the 2 black holes closer. By the way, if I'd start off with a D much larger, then I would just get the 2 individual black holes and they would not be these common motzes at all. Okay. So, but we want to investigate the properties as I make now D smaller. So this is D a little bit smaller than the previous one. And here what you find is that the green one is now much more deformed. So this one is now quite distinct from the blue one. The blue one becomes more symmetric as we make D smaller. So that refers to the fact that the final black hole, if you wish, in this case, is eventually going to be a Schwarzschild black hole. But the inner common mode, the green one, becomes more and more distorted. Okay. This is now the case when D is 0.4, still smaller. So as you can see, the blue one now really is almost a perfect sphere, while the green one is extremely distorted. And I should say that the red and the magenta one, they are more or less unchanged. They do change a little bit, as we'll see in a minute. But at this stage, they're not very highly deformed. And starting from this point onwards, to locate the green one really relies on our numerical methods here. It's really hard to find by other methods which rely on the star-shaped property. So this is now going further, and you will see here that D is 0.25, and the green one is now extremely distorted. There's one more thing that happens here, which is maybe not evident to most of the audience, which is that these surfaces are in fact minimal surfaces. So these are surfaces of minimal area. And it turns out that in this context, these surfaces cannot touch. So no matter how small I make D, it will be the case that, for example, the magenta and the red surface, they get closer to each other, but they cannot touch each other. Okay. So something has to then go wrong, right? Because the one puncture is centered, the red one is centered on one puncture, magenta one is centered on the other puncture, I'm making the two punctures closer to each other. So then it should be evident that the red and the magenta surface should get extremely close to each other, but they still cannot touch. On the other hand, the green surface has to cover sort of both of them. So it also cannot touch the red and the magenta one, right? So you can see that in this setup, something has to really go wrong, or not wrong, but interesting, let's say. And this is an example of that. So in this figure, the red one is, now it starts to get deformed. So it has this dimple on the top. The other one is, still remains a sphere. While the green one, it's not evident here, but it's actually not touching any of them. It's extremely distorted. And this is a close-up of what is happening at the sort of the neck of that surface. So the two motzes, the red one and in this case, the green one, the light green one, they don't touch each other. They get very close to each other. And the interesting one is this dark green one here, which is extremely distorted now. So you can see that it has a neck which is almost pinching off, but not quite. And here D is now 0.16, so much smaller than before. And this sort of is a summary of what happens here. So let me just summarize what's happening here. So it is for large D, I only have the two individual motzes, S large and S small, as it's called here. At a critical value of D, I have a common horizon, which splits into this inner and the outer portions, so S in and S AH here, as it's called for the apparent horizon for the inner mods. As I decrease D further, this inner mods becomes more and more distorted. Now, below a certain point, if I make D below a certain threshold, in fact, a little bit below this one as shown here, I can no longer find this inner mods. You could say, well, maybe the numerical method doesn't work anymore, and that might be true. But it's also the case that below a certain D, in fact, even the S large, the larger one, the red one, also doesn't exist anymore. And in the limit I make D very, very small, only the apparent horizon is there, and the other smaller black hole exists. Okay. Again, I could say a lot more about this, but I will in fact stop this discussion here and go on to other properties of this thing. So this is now related to this work of Anderson, Mars, and Simon that I mentioned before. So there's one. So this refers to what is called the stability parameter. So let me just tell you what that is. Okay. So let me just go back now to this discussion of the existence of these mods. So as I said here, as shown by Anderson, Mars, and Simon, if this mods is stable defined in this sense, it will continue to exist smoothly in the time evolution. And they define this notion of stability by using this expansion of this deformation. It turns out, in fact, that you can convert this to actually an elliptic operator living on this mods in the following way. You define an operator L, known as a stability operator, in the following way. So this L acts on functions living on a mods, and the definition is as defined here, which is L acting on F is given by the variation of the expansion as by function F multiplying R, right? So F times R, that vector, is the deformation vector. So that is the vector that defines the deformation of the mods. Okay, and delta FR is the sort of the thing that modifies the expansion. Okay, so this, in fact, it turns out is a nice definition of a stability operator living on two-dimensional mods. And as it turns out, that the proof of Anderson, Mars, and Simon refers to properties of this elliptic operator. So if this operator is invertible, in other words, if its spectrum doesn't contain zero, then in fact the mods evolve smoothly. And the stability parameter can be said to be the lowest eigenvalue of this elliptic operator. So if that's lowest eigenvalue, which in this case turns out always to be real, if it happens to be positive, then in fact the mods is stable. and the evolution proceeds smoothly. So we can define a stability parameter for this black hole as the lowest eigenvalue of this operator L. Okay. So what is now shown here in this plot is how this stability parameter changes as I change d for this common horizon. Okay. So let me just walk you through what is being shown in this plot here. So first of all, the different lines refer to sort of different configurations. So I showed you results previously for given mass ratio 1 to 4. This shows you the mass ratios for 1 to 5, 1 to 4, 1 to 3, 1 to 2, and so on and so forth. For each of these cases, I have two branches of the stability parameter. One is for the outer mods and the other one's for the inner mods. So focusing, for example, on the blue one here, which would be the mass ratio 1 to 5, the upper branch is the apparent horizon and the lower branch is for the inner mods. So you can see that, in fact, when this common horizon is formed, that is exactly, it's always formed with a zero stability parameter. Right? Eigenvalue is precisely 0 in that case. But it then bifurcates immediately into an outer inner branch. The inner branch has negative eigenvalue, the outer branch has a positive eigenvalue. So this sort of describes this bifurcation process by which a new mod is born, and in a nice mathematical way. And this is generically true. For each of the cases, for each of the mass ratios, each time I have a new horizon that is formed, it is formed in this bifurcation process in which the stability parameter is initially 0 for the common mods, and then it branches off into inner and outer branch. So in fact, again, I could say a lot more about this, but in the interest of time, let me go on and let me sort of talk about time evolution in this case. Okay. So we studied the initial data and we studied sort of interesting properties of mod system initial data. Now let us do something more interesting. Let us now evolve this in time. So then what will happen? Well, the two black holes will evolve in time and they'll merge. A common black hole will form. And then at the end of the day, I will only be left with a common single black hole horizon. And in this case, I just have two non-spinning black holes head-on collision. So in the end, I should get just a single short shell black hole. Okay. So let us see how this happens. So our goal is then to start off with Brilliant-Quiz data and then evolve it. And then what is new here compared to all other numerical simulations is that we locate these mods very, very carefully, and then we study its properties again quite carefully. So this is now the situation, what happens in the time evolution. So again, this should remind you of the previous sets of figures I showed you, except now this is for a time evolution, not just by changing this parameter d. Okay? And then here there's a critical difference, which is that when I changed the parameter d previously, I was just in the Brilliant-Quiz initial data, which was time symmetric. So the extrinsic curvature was 0. But once I evolve in time, that is no longer the case. So the extrinsic curvature is non-zero. So these are not just minimal surface, and now they're allowed to touch, and now they can in fact penetrate each other. And that is what we see here. So let us start looking at these figures from the left to the right. So now what is changing is the time in the simulation time. In the left one, the simulation time is 1.5. It changes to 5.5 in the middle plot and to 7.7 in the right plot. The precise values of what these times mean it's a simulation time, so it's not a coordinate independent thing. Just think of it like a parameter for time evolution in this case. So on the very left one, what you see again is similar to what we saw in the initial data. So I have the two common mods, so the red one and the magenta one, which are for the two individual black holes. And then as before, I have a blue one for the common horizon and a green one for the inner mods. Okay. Then this evolves in time. Again, as before, the green one becomes more deformed. It pinches off, it got the figure 8 structure, while the blue one becomes more and more symmetric. Okay. And in the middle panel, you see the case when the two individual mods are getting closer to each other. And the green one is extremely deformed. And you can see the neck is almost pinching off. Up to this point, this is sort of reminiscent of what we saw in the initial data. Then there's a dramatic difference that happens in the time evolution. That is the plot on the right, what you see there is that, well, the individual modules actually penetrate each other. So you can see the sort of the zoom shown in the little inlet in the right panel there, which shows you several interesting features. The first one is that I have the two individual modules, the red one and the magenta one, they penetrate each other. So they go through each other. Okay, that's fine. But what happens to the green one now? Well, the green one still exists, it still evolves smoothly, except that it now developed these loops in there, or these self-intersections. And in fact, this continues, and then if we evolve this further in time, the two individual modules go through each other more and more, and the loops become bigger and bigger. Okay, so this is a zoom of that situation even more up close. You see again that the red one and the magenta one, they're going through each other, while the green one is developing these self intersections. Okay, and then you can actually now construct this, evolve this smoothly in time, and we obtain at the end of the day this figure, which I will like to call as the analog of our pair of pants picture for the event horizon, except this is now for these modules. Okay, so let me walk you through this slowly. So time goes vertically up in this figure, and this is actually not just a cartoon, it's an actual representation of numerical data. So this is actually a numerical result of a numerical simulation here. Okay, so this is from solving the Einstein equations and by looking at the modules at each time and combining the modules to get a smooth surface here. So at the first time step here at t equal to 0, I only have these two individual modules. So the one again shown as a red and a magenta one, or the purple one here. So the evolution then starts, it proceeds in time, and the two modules get closer to each other. At a certain time, which I'll call here t bifurcate, there's a common horizon that is formed. So that is referred to as t bifurcate here. And at that time, then I have a common mods form, and a little bit later, that splits into an inner branch and outer branch. It's a little bit hard to see, but if you look closely, you see that the blue one is going outwards and becomes more and more sort of regular as later in time. There's an inner one as well there. If you look closely, you'll see it. So it gets closer and closer to two individual modules, and we show the cross sections of this in the previous figure. This is a 3D representation of the same thing. And the inner one exists as a smooth surface, and it goes closer and closer then to the two individual modules. A bit later in time, at a time called t-touch, in fact, the two individual modules then touch each other. That's why it's called t-touch. And at that time, then the green mods, the inner one, develop these self-intersections. So there's nice, interesting topological features that appear in the time evolution. Okay, so is this clear? So a lot of people have difficulty visualizing this. So please stop me if you have any questions, if I can explain any part of this better. Okay. Okay, so then let us see what happens to the area increase law here. Okay, so remember that one of the important things for the event horizon is that the area always increases. In this case, it's a little bit more trickier now, right? So now the question is the area of what? So if I look at the two individual modules and just track its area in time, I can do that quite easily. And it will, if I look at, for example, the red one, just red one by itself, that evolves smoothly in time, of course, and the area of also always increases for that one. Okay? Same thing for the purple one. So they evolve even when they intersect each other. I can still calculate the area, and that increases as you expected. And again, for the outer one, as long as I look at the blue one itself, that increases in time, and I can calculate the area of that, and that goes as you expect. The interesting one is the green one again. So at any given time, so I can calculate the area of the green one, and that, if I go forward in time, it in fact decreases in area. So that's a signature, in fact, that is not, it's a bit different from the others, right? And as it turns out, that in fact its signature is different. So it's not always a space-like surface, and that is the reason for this behavior. So how do we now think of the area increased law in this context? So let me now just propose one way. So on this plot here, I'm showing a few things here. So the curve in the red dotted one is the sum of the areas of the two individual monsters as they evolve in time. So the red one is A1 plus A2. And as you can see, it always increases in time. Okay. Then I can think about the blue one, the apparent horizon. So that is formed as at a time t bifurcate. And I can the blue dashed line shows its area as it evolves in time. And again, it evolves in the usual way, it increases in time. Okay. So the green one now is the one that is, again, let's call it anomalous. So it starts off at t bifurcate and then it decreases in area. Yes.
Sorry, I'm just going to ask you a question just to clarify. If you can just go back to the previous slide, what is the red? What is the red on this? The A1 plus A2, the I, which is increasing. Sorry, I didn't get that.
Okay,
This
good. So
red.
let me. Right. So you're referring to the red dashed line here, right?
Yeah,
Red
and I'm
dotted.
trying to see whether it has something. I mean, whether you have. I mean, this is just what you expect. Is it or?
No, it's a
Not sure.
calculation. So this is a numerical calculation here. So this is actual data now. This is not just what we expect.
Yeah, but what is that surface that
Yeah.
you're?
So A1 plus A2 is the sum of the areas of the two of the in this case the red surface and the purple surface.
Okay. All right. Fine.
So at
Okay,
so at any time, I get these two disjointed
sure.
two spheres, and then the red dotted line here shows the sum of those two areas.
Okay. Great. Thank you.
So this is what we would do for an event horizon, right? So for an event horizon before the merger, if I take a cross section, I would look at the sum of the areas of those two disjointed parts of the event horizon. So that is what is done here as well. Okay. So
Thank you.
that is a red dotted line. The blue dashed one is the area of the apparent horizon, as you expect. So that is the thing that is for the blue surface here. And as I go forward in time, as I go vertically up in this figure, that increases in the area. The green one is the anomalous one. So as I go forward in time, that in fact decreases in area. That is shown here as the green one, as a green surface here. Okay. So now the obvious thing we can do is to sort of change our sense of time on this green surface. So then I say, well, let us start off on the red dotted line. Let us proceed increasing along time as long as that red line touches the green one. Once that happens, let's go backwards in time along the green surface and then proceed then through the bifurcation and then back along to the blue surface after that. Okay. So follow the arrows in this figure here. So I start off going from left to right on the red one, and right to left on the green one, and then left to right on the blue one. So in this figure here, that corresponds to going forward in time, up to the point t touch, then going backwards in time along the green surface, then following the blue surface forward in time after that. Okay. And in this process, in fact, it is almost true, and this is the green one is in fact a source of headache always for us. This also makes it more interesting, which is that it might seem here that in fact along this sequence, which are called here sequence 1, 2, and 3, which is exactly following these arrows, that the area will always increase monotonically. That is in fact not quite true. So in fact, the green one, in fact, it has this little portion, in fact, which is not monotonic even in this sense. And it's all got to do with, the signature of this green one and its geometrical properties. Again, I could go into a lot more detail about this, but let me leave this as sort of an interesting thing for you to think about here. And let me then go on to other sort of interesting properties of this merger. So I told you about the stability parameter for this for mods. Then you can actually calculate the stability parameter also for these mods that we find in the simulation. And let me show you the properties of that. So this figure shows the stability of the lowest eigenvalue of that operator for the 3 different monsters, for the 4 different monsters. So for the 2 individual ones that are shown in magenta and in red, those are all positive, so it's all stable, it evolves smoothly, everything is fine. Then the bifurcation happens for the blue and the green one, again, as you expect. So it's born at 0 stability parameter, and the blue one is stable, as you expect, everything is fine. The interesting one always is the green one, this inner common mods, right? That, in fact, is unstable in the sense, and its stability parameter is negative, and it keeps on becoming more and more negative as we go on. You can repeat the same thing for what is happening at the merger. So then the interesting question is, well, when we have this these self-intersections forming on this inner mods, what is happening to stability parameter? Well, it in fact it diverges. So what is shown in this plot is the same as the previous, but for a larger range of time. And the green one is the sign is flipped, so you should think of it as being negative, otherwise I can't show it all on the same plot. So the green one is unstable, so it has a negative stability parameter, which in fact diverges at the time when the 2 mods touch each other. And again, there's a lot more to be said on this topic, and this is the full spectrum of this operator for the 2 individual mods. This is the spectrum for the apparent horizon, and you can see again interesting features here. But the most interesting again is this inner horizon. Okay, so just for fun, let me show you this, just to sort of impress upon you the complication of the geometrical properties of this inner mods. And there's again more I could say here, which is that in fact these are not the only mods that exist in this figure, and this in fact a whole sequence of infinite bifurcation that happens in this time evolution. And this is the process by which these 2 individual mods all merge, and at the very end I'm left with just a single common short shell black hole, which means that by the very end all of these complicated inner mods, they must all annihilate each other, and in the end we are just left with this common simple boring short shell black hole. And there's a lot of these topological features that happen during the merger seen in this for these mods as seen here. Okay, so let me actually then just stop here and show you some more figures of some other mods without describing what they are, just to sort of impress upon you the all. In this case, for example, you see these multiple loops forming. And let me stop here and let me just say that despite all the complications, there is in fact a connected sequence of mods that takes us from the 2 initial black holes to the final black hole. Then you can use it to construct what you might call the analog of the event horizon, or the pair of pans picture, to visualize how a black hole merge, or 2 black holes merge. There's interesting geometrical properties of the area and the physical properties of mass and angular momentum. In this case, not angular momentum, but at least the mass. And that allows us to connect physical quantities across, calculate them across the merger. And this in fact has implications of cosmic censorship and so forth. So again, I will not discuss this here, but just to sort of, again, show you the complications that happen even for the simple initial data that we looked at here. So with that, I'll stop and I'll take questions.
Well, thank you very much. Let's clap our hands for a very, very nice talk with some very interesting pictures. But I think, yeah, to imagine that these are sort of actually happening in evolution of these marginally outer-trapped surfaces, and whether what one can make of them even from an analytic point of view would be very interesting. So let me open it up for questions. We do have a question from Akshay Kumar, who I think that it may be a better idea if you can actually ask your question, Akshay. Can you perhaps?
Am I audible?
Yes, you are audible. Yes. Please go ahead.
Yeah. So my question was, how modes are
Can you
better?
ask? Can you?
How modes are
Can
better?
you speak?
Yeah. Am I audible? Right.
Yeah. Can you speak a little louder?
Okay. how modes are better to study horizon compared to marginally trapped surfaces? Can you elaborate a little bit? Secondly, we know dynamical horizons are positive space-like foliation, and null case represent isolated horizons. So what if we have negative or time-like foliation? What will going to happen with horizon in this case? Are they still stable?
Okay, so a lot of things in that question. So the first thing is, I guess, just a clarification. So when I say mods, these are all marginally outer trap surfaces, right? So these are all of these have zero expansion for the outgoing null normal. Okay. So by a margin trap surface, we also then say that the other expansion has to be negative. So that is that, as I said very in the very beginning, that is not such an important condition. So that in fact it is not true that the uh, the expansion of the ingoing null normal has to be negative. In fact, that is not true for the green surface here at all times. Okay. So I would say the distinction between a MOTS and a MTS is just a technical thing regarding this ingoing expansion, which is technical, but it is important though. But it's at that level. So physically, these are still the same. It's a question of definitions, and this is we're looking at, I would say, the same kind of surfaces here. Okay. Now the other part of this is important, of course, which is that as Akshay said, for the dynamical horizon, it's a space-like surface, and that is true in the in this figure. So if I go back here to this figure, so the blue surface is in fact space-like. It is not always, so the very beginning, it is not the other expansion is not negative, so it is not a marginally trapped surface at the very early part of this bifurcation, but that's again technicality. Important point is it is always a space-like surface. Okay? And the same holds that for the red and the magenta one. So they are also, the individual modes are also space-like. And as always, the complicated one is the green one. So it is not space-like always. It is, no, it has, in fact, time-like portions on it as well. And the answer to your question of whether these are stable or not, so that the question is, what do you mean by stable? It's not stable in the sense that the stability operator is not always, eigenvalue is not always positive. So it is not, you cannot think of this as, as being, if you deform this slightly outward, it is not that you will find a untrapped surface always, right? It is not stable in that sense. Nevertheless, the evolution still continues smoothly, and you get this smooth three surface as I showed here. So I would say that when you say what will happen, well, what is happening to this green surface. That's an example of what can happen. It's a lot sort of less, let's call it well behaved than the other monsters here. But still, you can study its properties, and you can look at its evolution, you can look at its geometric properties and physical properties. But it is a lot more complicated. And its area increase law is the thing that is perhaps the most vexing one for this purpose here.
Okay, thank you.
Are there any other questions? So you maybe if there aren't any others, ask a very general one, but so you talked about this work of Jaramillo and I forget who else, and Ansorg. Have they also looked at, so that's presumably analytic work on these, on the behavior of these marginally trapped tubes?
Yeah, so that's also in fact numerical work. So, but it has a lot of analytical component in it.
See.
So it is numerical work, but what they were trying to do was to, if I recall correctly, so now what you could do is to say, well, a lot of the complications we see here are because of the assumption that the data is time symmetric. So in that case, these mods are minimal surfaces, and therefore they cannot touch each other. So you could try to study this, sort of say, well, let us now relax this condition of time symmetry. So let us look not just at Brill-Lindquist data, but let us look at Bohr-New York data, for example. And let us look for the motsas in that case. So then, in fact, they could touch each other, right? Because they're not minimal surface in that situation. So if I recall now, I think this was Jose and Marcus, they were studying that situation in that paper.
But it seems a reasonable thing to say to start with time symmetric data, because I mean these are, I suppose, numerically easier to simulate. Is that the case? Or
no, numerically speaking, I think okay, once you get the code in place for looking at extrinsic curvature, then it is not really more difficult to find the motsas themselves. So
right.
I think it's not really that much more difficult. So I think what they did was quite reasonable, and I think it's maybe we should revisit that at some point.
Okay.
But we are sort of getting across. So in our case, we do time evolutions, so at any later time, the extrinsic curvature is non-zero, and so data is not time symmetric at that later on.
Very interesting. Yeah, thank you. Are there any other questions? Anything in the chat box? If not, let's thank Badri for a very nice talk. And thank you so much for making the time to be here with us today. I know that you had to shift your schedule around, but I hope it was worth your while doing this. And the talks will be available on the YouTube channel, I think simultaneously, but edited versions very shortly. So let's thank Badri once again for this very interesting and thought-provoking talk.
So thank you, Sumati. And again, I want to it's a great honor to be in this conference. And again, let us definitely remember the works of Ivan Choque-Bruja and how important they are to all of these developments. And as I said, I couldn't refuse talk in such a conference. So thank you for that.
Okay, that's great. So I hope we'll see all of you here this evening again. It starts up again at 7:45 Indian Standard Time. And let me try to see what the times are for the other. Unfortunately, I don't have it up here with me, but yeah, let me read out the other times that are there. So 7:45 Indian Standard Time, 3:15 CET, 2:15 UTC, Eastern Standard Time, 9:15 AM. And that will be Lydia Bieri and Mihalis, followed by Mihalis Daformos, which will be last session of our meeting. So thank you all for being here today. And thank you again, Badri, for a very nice talk. So we'll see you this evening.